All right. So I talk about thanks for inviting me, and I'll be talking about one of the deepest challenges of x86 security and how the PC industry is trying to address it. If you're doing offensive research, you will discover an interesting attack surface against the most privileged software on x86 under the latest security architecture. And if you are doing defensive research, you will study interesting, unique security architecture and the data source you can consume to provide better visibility into your system around the system and boot security. So SMM, System Management Mode, is an x86 processor operating mode. It has a higher privilege than kernel or a hypervisor. And software running in this mode it's not controlled by any security hardening or security policy enforced by hypervisor or kernel. This kind of software is called SMM modules, and it's reachable from the kernel, so like this. So if there is a security vulnerability in SMM modules, it can privilege its privilege from kernel to SMM. And then, for example, you can tamper with a hypervisor. And also, even worse, the SMM software is historically, in terms of security, written poorly. So it's been exploited repeatedly more than a decade, probably more than 2 decades. So to combat this situation, the PC industry introduced a radical software architecture changes to deprivilege SMM modules. So the high-level idea is that if the SMM modules are running in isolated user mode privilege, they cannot do a really bad thing until the exploit first privilege its escalation from user mode SMM to kernel mode SMM. So you cannot tamper with hypervisor or anything really bad. So AMD calls this architecture as a SMM supervisor, and Intel calls this new architecture as Intel System Resource Defense. So let's dive into how this architecture works in practice on Intel platform and what attackers and defenders can do with this architecture. So this is historically how the SMM module ran. A special type of interrupt called SMI, System Management Interrupt, gets triggered by, for example, kernel or a driver. So the processor switches its mode from non-SMM to SMM and start executing an entry point code. The SMM entry point will execute other SMM module which actually implement the handler for the given SMI command. So it does actual job. And once all work is done, processor will return execution from SMM to non-SMM. So in this case, kernel or a driver. And notice that all of this work is done in kernel mode, SMM kernel mode. So this isn't great because typically in one system, like laptop you have, typically have like more than 100 of SMM modules, which may implement different handlers. So it's analogous to like having a dozens of syscall or ioctl handler that is written by non-security, non-software giant, and it has never been really reverse engineered by security researchers. And even worse, the SMM doesn't have the modern, well, not necessarily modern security mitigation features. Like it doesn't have the ASLR, and it doesn't even have a stack canary. So situation is definitely very exciting. So in the ISRD security model, well, the architecture, the SMM modules are pushed down into user mode. So just as a clarification, SMM module, well, SMM is more like a Boolean flag in a CPU, meaning that on the processor can be in SMM kernel mode or SMM user mode, kind of like being normal kernel mode and user mode. So it's a separated concept from the ring level. And to take advantage of all SMM powers as an exploit, the CPU has to be in kernel mode SMM. So If the SMM modules are deprivileged into the user mode, then it cannot do really bad things. So in the ISRD model, there are 3 modules. Well, all modules are pushed down into user mode SMM. And what happens when the SMI happens on this model is that the SMM module gets executed in user mode. And then when the SMM module in user mode tries to execute the system resources, like MSR registers, the processor causes exception because it's user mode. Then SPS, the other module running in a kernel mode, will catch the exception and consult the policy on there and checking if that operation should be allowed for the user mode SMM or not. And if that's allowed, the SPS here will perform the same operation on behalf of the guest and on behalf of user mode SMM and return the result. If the operation shouldn't be allowed for the user mode SMM according to the policy, system will basically reset. In other words, if the SMM modules were written within what policy allows, those SMM modules just work fine, even though they are in a user mode. And if it gets exploited and the exploiter tries to do something beyond the policy allows, then it doesn't work because it would be blocked. And the policy information over there is customizable from OEM for the OEM. So it helps them to convert the existing SMM modules into kind of user mode without too much effort because it's customizable to OEM, so they know what resources your module needs to access. But here is a question, what if the OEM put a policy saying, I allow everything, whatever you can do, right? That's what OEM might do because it makes their job easier, right? So a related question is, how do we know what policies are actually in effect? So this is where the PPAM on this diagram comes into play. This is the other module in SMM kernel mode. So PPAM as PPAM will provide an interface for the non-SMM software to query the policy information that is active. So the non-SMM software can query information and report if the system state, well, policy is good or not. But the other also related question is, what if an operating system gets actually compromised? We get the information and operating system gets compromised, and operating system may say, oh, your system is perfectly good, even though if it might not. So we don't want that. So this is where the next big security architecture changes or updates playing the role. So the next architectural changes are called ISSR, Inter-System Security Reporting. So it provides 2 major functionalities or properties. The one, your SMM software can query the policy information from the SMM by talking to PPAM in a secure way. And the second property is that you can keep the information you received in regular memory on non-SMM world in a tamper-detectable manner. So by combining those, our software can basically use the policy information later and without worrying about if it's actually tampered or if it's authentic or not. So the first one is achieved by, first property is achieved by PPAM, returning the policy information only when the system integrity has been verified. And it's done by using the other hardware feature called intelTXT. So with intelTXT, a special instruction called getSec is when that's executed, the processor state will be reset into clean state and start executing the modules you pre-configured, pre-specified. And before executing those modules, the hardware platform will cryptographically measure the integrity of those modules. And if the hash value computed by this process doesn't match with the expected hash value, the system will just reset. So in other words, after getSec instruction, if your module gets executed, you can tell your module, integrity of your module is not tampered with, and some other modules too. Also, TXT measures PPAM over there. So this way, you can tell your module is good, and PPAM also is good because TXT verifies both integrities. So you can talk with your module on the left side, can talk with PPAM, and query the information. But also, you need to make sure that the information you got from PPAM, which is in SMM, and you got information in the non-SMM world, you need to make sure that the information will not be tampered with. So ISSR achieves, ensures the integrity of this information using TPM. So TPM is a tamper-resilient module, and it keeps track or keeps record of system boot phase as a hash values. And the data stored in TPM will not be overwritten until the system resets. So you can assume the value stored in TPM hasn't been modified since it was written. So with these assumptions or with these promises, ISSR basically hashes the value, hashes the security policy value, and then stores it in TPM. And the value stored in TPM is not usable because it's just a hash value. So it will also store that the hash policy information, security policy information, into the other data structure called TPM event logs. So TPM event logs are just a data structure on regular memory, but it is structured in a way that if you rehash the content of this data structure, you should be able to get the same hash value as in the TPM. If you recompute the hash of these TPM event logs, and if it doesn't match, you can tell the value stored in this TPM event log has been modified. So you can tell the data is not authentic. If it does match, you can tell the security policy data stored in the TPM is authentic. So you can confidently use the policy information. So to make the discussion a little bit more concrete, let's talk about how this system works with Windows or on Windows. So the ISSR is called SMM firmware measurement, which is part of the system guard secure launch feature on Windows. So at the boot time, Windows.exe will execute get-sec instructions and start measure the launch. So Intel TXT process, Intel TXT. And then processor after this executes the TCB launch. So TCB launch is the pre-configured module that executed after the get-sec. So TCB launch knows when the TCB launch gets executed, this process will know he is good. He's not tampered with because TXT should have verified it. Then TCB launch will talk to PPAM to get the policy information. And also, it converts the policy information into the other value called SMM isolation level. So the idea is that SMM policy information is a complex data structure. So it's hard to use for the most of other software. So the idea is that let's analyze the policy information and convert it into just a single byte value showing the level of security policy. So the higher value, the better or more secure. So this value is called SMM isolation level. And TCB launch saves it into TPM and also TPM event logs, which is on Windows called WBCL, Windows Boot Configuration Log. That is accessible from the API, TBS API. So for defenders, as a call for actions, for defenders, look into WBCL. The WBCL contains a lot of information about the boot state beyond just SMM isolation level. So it will provide great visibility into how the system has booted. And for security researchers doing offensive side, SPS SMM policy shim is the obvious target for research because it's running in SMM kernel mode and takes input from user mode SMM, evaluates policy, and emulates the operation. So it's an obvious target. The other interesting target could be the policy itself. So the customizable policy means some OEM may configure policy in a way that's not secure, entirely secure. So there is already a great talk around this like policy evaluation against the AMD implementation. So if you are interested in, check it out. Finally, the bugs in PPAN would be interesting because it's the other SMM module running in a kernel mode. But the exploitation of that would be a little more difficult because the most of the code doesn't run in normal world. All right, so this is it. There's a lot more details I can talk about. And this QR code is a link to my blog post explaining much more details about these architecture changes and research ideas. And so you can check it out or just talk to me after this. So thank you very much.